Hi, my name is Kevin Starr. Today we're going to talk about statistical analysis. This is really at the root of literally everything we do when it gets into data processing, data analysis, signal analysis. Big data is the buzzword today. How do you look at data? How do you shape data so that you can have it tell you its secrets? It all has its roots in this particular discussion, statistical analysis. And that's what we're going to talk about. We've taken this data and mapped it into our signal analyzer and our data manager and our loop tune application. This is the kernel knowledge that goes behind our channels and the KPIs, our key performance indicators. So this is the stuff that I like to say is the root. This is the kernel. If you can understand this or start to understand how you can use these terms, then these are building blocks for the more advanced things that we will talk about later on. When we talk about statistical analysis, one of the things that makes it confusing is the data. Sources of data, data sampling, sample frequencies. And really what we have to realize is what's the problem you're trying to solve, and then match the data resolution to that problem. And that's what you'll see here is, are you dealing with the DCS? Are you dealing with variability data, quality data, profiling data? Do you want data every 5 seconds? Do you want it in the machine direction or cross direction? Or do you want to have it in grade dependent? Or there's whole different answers to the type of problem you're trying to solve. Then you get into the sample time. When I first started, 100 hertz, 1,000 hertz was unheard of. If you get a 10-second update, that was great. Well, now we can get things at 1,000 milliseconds. So, let's just sample 1,000 milliseconds for 10 hours and see what happens. Problem is your file sizes are so gigantic you can't analyze them. So you really need to kind of understand where's the problem I'm trying to solve and what frequency do I want. And the answer is different depending upon the data source. High speed is another thing. Is that 1,000 hertz or 1 second or 1 hour? I don't like to use the term high speed analysis because it's relative to the application and the industry that you're working with. So try to stick with sample times, and we'll get into data sources and how to do that. You get into filtering, anti-aliasing, digital reconstruction. That's a whole nother subject. But I wanted to at least alert you to the fact that, let's say you're sampling every hour and you have a problem that's happening every 10 seconds. You'll never see it. Actually, it'll alias into something else. So I'm just bringing that up, that statistics are functions of the resolution of the information that you're loading into it. And we're going to assume in this one that we've got the right resolution. And what we're going to do is add statistical analysis. So I tried to piece this puzzle and say there's different classes of analysis. Statistical analysis is what we're going to cover in this session. 4A analysis has to do with things that oscillate, and identification is causality. Is two things occur, are they related or not? So we're going to first of all basically examine one signal at a time, signal analysis. And we're going to understand these terms: average, mean, max, mode, range, variance, sigma, coefficient of variation, skewness, kurtosis, histograms, correlation, covariance, performance index. What is all that stuff? Well, that's what we're going to go through here. It's kind of daunting, this task, but they're all kind of related. And so they'll all build in each other. In the next session, we will talk about 4A analysis, which actually is one of my, I enjoy that one, is cyclic reduction, variability, period, amplitude, there's Nyquist periods, fundamental frequencies, the 4A series, 4A coefficients, amplitude, power spectrums, accumulated spectral density. Woo, what's all that stuff? Well, that's for the next session on 4A analysis. And then we get into identification, which is bump test. If you went through the process tuning, we covered that. But there's also cross correlations and inner loop causality, and that would be for a plant-wide disturbance analysis. But most of that particular discussion there deals with tuning, and that would have been in one of the other videos on single loop control methods. So in this series, we're going to talk about statistical analysis. So we're going to talk about a sine wave, define a sine wave, get into statistical analysis. The trick is to come up with a number. I like to think of it as a filter, like a histogram or a sigma or skewness. There are different mathematical formulations that you apply to a series of data to tune your eyes to see different attributes in the raw data. Once you start knowing how to calibrate your eyes, some of those you don't need them so much, because you can look at it and say, well, that's skewed, or it's got a kurtosis of -1 or whatever. We'll talk about that. This allows you the ability to tune your eye to large amounts of data. Then we'll go through statistical process control. That's not as popular as it was years ago, but we'll go through it because it fits in this space. And then there's auto and cross correlation, which has to do with how well the signal looks compared to itself at different time periods. And then performance indices, which are different ways to measure performance. So those are the way we're going to break this particular discussion down. A sine wave is, and we could use a cosine wave or a sine wave, but for this I'm going to take a sine wave where it starts at 0 and it goes up and down. So we have an amplitude, and you'll hear people talk about amplitude or peak to peak. Peak to peak is 2 amplitudes. The peak is the top of the curve and the bottom curve. Peak to peak or half to peak would be the amplitude. So if you look at the mathematics, and this is something I would recommend if you want to go to Excel and build a sine wave, this is the equation. Put in like 1 through whatever, and then 2 pi is 3.14, and I'm showing 100 samples. So this would have 1 period in 100 samples. So you could do that in Excel and make it. And then this is your amplitude. So this is what this would look like. There's 100 samples. It went up and down with an amplitude of 3. That's just how you would do it. So I'm going to use this example. So now I have a sine wave. What can you tell me about it? What's the average? What's the mean? What's the DC component? What's the range? What's the variance? What's the sigma? What's the skewness, the kurtosis? Those are all numbers that represent the data set. And once you start to see how those numbers are built, you can basically look at the numbers and know what the data was doing. That's the trick. If we take the average is what's called the median, or the mean, or the DC component. You just simply, and that's right, we're going to show you some math here. So these are the symbols. X represents the measurement. X1 sub is the first measurement, second measurement, third measurement. So if you were in Excel and you were to pick all those rows in that column and sum them, this is what you would get. So you take the sum of all your parameters and divide by the number of parameters. That's what's called the average or the mean value, or some call it the DC. In this case, it was really easy to see. It's 0. It started off at 0. But this little funny squiggly thing is a summation sign. It's just it mathematically says take the series of numbers wherein we sum it from 1 to how many points there are in the data set. That's how you read this summation. So an average is equal to the summation of the parameters divided by the number of parameters. That's the average. Now what we're going to do is realize that there's mean, there's median, and there's mode. Mean is the average. We just talked about that. But what's the median and the mode? The median is referred to as the middle number in the data set. Which, if you want to sort, now go to your Excel and sort them, high to low, and find the middle number. That's what the median is, the middle number of the sorted data set. The mode is the most frequently occurring number. So here's a quiz for you. If you have a normally distributed data set, how are the mean, median, and mode aligned? They're the same. That's another, you can look at the normalcy, and we'll talk about statistical normalcy here in a minute. But if the mean, median, and mode are the same number, it's considered a normal data set. Okay, now range. Range is simply the highest point in the data set minus the smallest point in the data set. It's the range. Range is a good indicator of the spread of the data. And years ago, when things were a lot more analog, it was a very good representation of the energy in the system. Today, with noise or noise spikes, you can get a spike that would take your range very big, which it didn't really happen. So you don't see range used as much, but you see variance and sigma starting to show up. But that's range. Now variance, this is where some math starts to come in, but what I'm trying to do is break it in parts here. Is the equation looks a little much as the variance is equal to the summation of this x bar is the average. So I take the average out, so I normalize it, so I subtract each point from the average and square it. I add all that up and divide by the number of samples. So what it looks like in a trend is this. Here's our original data set. So if the first thing I do is square each number, it basically makes everything positive. Okay? Now I have these twin peaks here, and if I shade all this stuff, so what's the average of those peaks? That's your variance. So the variance is the average of the squared signal with the mean removed. What I'm trying to do is in this particular case, the variance shows the square of the error and the average of that. That's variance. Now what's interesting is the relationship between variance and amplitude, because I'm showing a sine wave, and this will come up when we get into the Fourier series. This is how the Fourier series works, is it calculates the variance for a data set based upon the sine wave and the cosine contributions. But if you look at this, if our sine wave was bigger, wouldn't you expect the variance to be bigger? And that's true. The signal that the sine wave most looks like is the one that's contributing most of the energy, or the most variance. So variance is a number that represents the energy or the spread of the data. This particular one is showing that if I take the amplitude squared divided by 2 is equal to the variance, or the amplitude is equal to the square root of 2 times the variance. And you can see that right here is as the amplitude goes up, the variance goes up, but they're related together. Amplitude squared divided by 2. We're going to use that again in the Fourier analysis. That's a kind of a breakthrough when we talked about Fourier and how he came up with his coefficients. The problem with variance is it's a squared unit. So if you're talking about flow in gallons per minute, your variance will be in gallons per minute squared. That's kind of a hard number. So what we do is we take the square root of that. And that's what you'll hear referred to as sigma, or it's called the standard deviation. The standard deviation is simply I shouldn't say simply, it's just the square root of this equation. So this equation inside is the variance. The square root of that is the sigma. So sigma squared, if we square it, we've got variance. So variance is equal to sigma squared, where sigma is equal to the square root of the variance. Now, why do we use sigma? Well, sigma opens up a whole list of things regarded to normalcy of the data. Normalcy is defined by statisticians. So here's what we're going to talk about in just a second. There's another one we talk about. It's called coefficient of variation. The coefficient of variation is normalized, and it's equal to the sigma divided by the average times 100. That's one of the issues. If you look at the variance here, we are normalizing it by the average. So what happens is if you have something that runs around a level of 3 or a level of 300, your sigmas might look a little different. So you want to try to normalize them. So the COV, or coefficient of variation, is the sigma divided by the average. And that allows you to, and then it converts it to a percent. So basically that's what the coefficient of variation is doing, is taking your sigma and converting it as a percent as a function of the average. There's not one statistic that is the best, and I like to present a few, and then they're like screwdrivers on your workbench or tools, and you always tend to go to the ones you like. I can't tell you which ones you're going to like, so I'm going to show you the ones that are available, and then you'll start to migrate towards different signals or different algorithms. The nice thing about sigma, or standard deviation, is it defines statistical properties that have to do with normalcy. And I'm going to explain that here in just a minute. But you may have heard of a Gaussian distribution, or a bell-shaped curve, or a normal distribution. The standard deviation is a number that actually quantifies where the data will be found from a probability perspective. So when we look at this, a normal distribution, and you'll hear it talk as a Gaussian or a bell-shaped curve, it literally looks like a bell. You see, it looks like a bell. And the center of the bell on a normal curve, the mean, median, and mode is right in the middle. Then we start going away from the mean, or the middle, and when we get 1 sigma away, plus or minus 1 sigma, 68% of the data. So if I had 100 points and I have a sigma, 68 data points will be right in the middle, okay? Plus or minus 1 sigma. 95% of those data will be in plus or minus 2 sigma, and 99.7 will be in plus or minus 3 sigma. So that's what a normal distribution is. And there are nice attributes of a normal. It's predictable. You kind of know where it's going to be. And when a signal just sort of floating around is going to have very close to normal characteristics. So if we can measure the normalcy of a signal, we can tell if it's working. Once we start having, if we have an actuator at a limit, or we have a control that's oscillating, or nonlinear attributes being introduced to the process, you no longer have a normal curve. And so it starts to shift to one side or the other, and that opens up where we're going next. Skewness is a definition of how the data is shifted. So, and I'll show you some examples here in just a minute. But skewness that always gets me confused is whether it's plus or minus. But the math is a big number. I wouldn't worry about the number yet, because there's a lot of algorithms that just calculate it for you. But what we look at is which tail of the bell-shaped curve is longer. So whichever tail is longer, you know, it's either plus or minus. So what we have here is a skewness is positive because the positive going tail is bigger. It always kind of it shifts to the left, which is in my mind negative. But the powers that be said that the positive going tail, when it shifts to the left, is positive, and if there's more data on the left side, then it's negative. So that's saying that and usually I'm hitting a mechanical. Well, I'll show you. This is like a one-sided bump test, or you know, asymmetric noise. That's an example from a different industry, but it's asymmetric noise where it's just one-sided. Or you'll have a measurement that's out of range. You know, it sort of keeps hitting a limit. So it looks like somebody cut. You can look at the raw data. It looks like somebody took scissors and cut the top off, so you have these flat spots. So the data will be skewed in that direction. Skewness is an example of a mechanical constraint or something in the data that is not normal. So that's what we have that ability, is you calculate the skewness on all your data sets and you sort it, and you can tell the ones that have some sort of a mechanical problem just by doing this statistical algorithm. Kurtosis is how skinny or fat your signal is as compared to the normal curve. If your kurtosis is large, that means you have an abnormally large amount of numbers right around the average. If your kurtosis is small, that means you have a lot of data at the lobes and not very much in the middle. I recommend that you calculate this if you're doing any kind of performance projections and you use the sigma and project reductions variability, because that's the whole claim to fame of process control, is you can reduce the spread of the data. And that's true, but if your data is highly influenced through kurtosis, you may be looking at noise that is causing your sigma to be as big as it is. So I recommend calculating the kurtosis to see how normal your distribution is. Because if you already have a bunch of data in the middle and you have some outliers, control can't fix that. That's a different problem. So that's why I like to use kurtosis to calculate that. Again, you can see the equation is pretty intense, but don't worry about that. There's algorithms that calculate that for you. Now, here's some examples of kurtosis. You know, a sine wave will have if you think of a sine wave, most of the data is at the top and the bottom. So that's what it looks like, is you have a low kurtosis. Noise spikes, where you have a big spike, it will push it the other way. So you can start to identify issues. And this is the building blocks of the loop performance channel, where we look for signal conditioning and disturbances and control. We do this stuff behind the scenes, and then we sort it to you as the user in order of these abnormalities. So on the loop performance, you can look and you can see the skewness and kurtosis, and you can tell, ooh, so this is where this came from. We see patterns in the data, so we pull that into the loop analyzer, and we can actually align these statistics with known problems. So we can sort them and present them to you. But if you understand the statistics under the hood, you have a little more confidence in what those KPIs, those key performance indicators, are telling you. Now here's an example where we've just collected a raw data set. It's what data looks like. And so here's what you can see it floating around. So I can look at that and I can see I've got an average of 42. Okay, I've got a peak value of 43 and a minimum value of 40. Okay, so it's got a range of 3, I guess, and an average of 42. But is that really telling about the variance and the skewness and the kurtosis? No. So that's why I'm just showing you here. You very rarely would do this, but the variance is just, we're squaring each value. We're removing the average and we're squaring it. So you can see the pink there. And this is showing the sigma limits, the 1, 2, and 3 sigma. So you can see this is getting close to what's called a control chart. So we take the variance and we calculate the sigma, and then plus or minus 1 sigma, remember 68, plus or minus 2 is 98, and plus or minus 3 is 99.7%. That's pretty close. Now, a control chart looks like, and this is now, we use the raw data to calibrate our control chart, and then what we're trying to do is alert the operator that something's broken. So in the world of statistical process control, it's called SPC, are these control charts. And they're looking at the normalcy of the data, and if the data becomes abnormal, something's broke. This is Deming's theories on statistical process control, and it works really good when you're measuring widgets or even continuous process control. Is you kind of benchmark the normalcy, and when the normalcy changes, something's broke. You need to stop and fix it. That's the concept of SPC. So what we have are these control charts. So you can see here, typically they'll weight these limits to be a +1 or a +2 or a +3 that happen to be at the 1, 2, and 3 sigma limits. So what we have is, if you look in this range over here, your signal, if it's normal, it's sort of floating above and below. So every time you go above, you add 1. Every time you go below, you subtract 1. So if you accumulate that, it doesn't do anything. Now, if we start to go up, our process, it's no longer normal. So we start adding it up. All those +1s, when it crosses over the 1 sigma threshold, we can send up an alarm. Hey, something happened. And then we may have high, medium, or low, medium, and high alarms or thresholds. And if the corrective action doesn't solve the problem, it continues to go. Once we cross the 1, we start adding 2s. So the slope of the error, and we get it faster. So it's a design to give you a little bit of freedom to wiggle around at the lower levels. If you start wiggling around the next threshold, you're going to get alarm faster. And if it goes to the third one, it's going to happen very, very fast. So it's really beneficial if you have spikes in the data. You don't want to be alarming every time you have a spike. So you want to make sure that you alert the operator. And that's where SPC, if you're going to stop a production line, you want to make sure you've had the problem more than just once. And that's where SPC can come into play. This is a very fast introduction to SPC. There's books written on it. But this is the concept you can see here is I'm showing the time to make an alarm. So right here, and this would be like the alarm limits. So this is my data rolling across. And you can see I'm adding 1, and eventually I trigger my alarm threshold. And so at that point right there, I would give an alarm. Boom. So this has been trending off for a while, but you are sure it's trending off when you get an SPC alarm. This particular example, you can see that it jumped past the 1 sigma and up to the 2 sigma. So it started adding, so you can see the slope. So the alarm occurred much faster because we accumulated more. We weighted the error more once it crossed the 1 sigma limit. Okay, so you got the alarm faster. This is a case where there's a problem, but in SPC it wouldn't catch it because see, you're adding and then you start coming. So you add in this range, you subtract in this range, you add in this range, you subtract in this range. So if I look at the alarm limits, I just keep, it never would alarm. That's why there's no one silver bullet that answers everything. I like combinations. So SPC is good when things are drifting off. You can be told. When you have issues like that, you need to look at a different algorithm to try to find this is what a bad valve looks like, or the cleaning issue. Here's an example where alarm limits. So physical limits on the measurement for this type of a problem are probably important. Where SPC, we had this problem, but it never triggered because it didn't stay in that state long enough. But if I just had a high limit, high, and a low, and the measurement crossed that, I would have got an alarm. So you can see in this case, you as an operator have to decide, do I want to know about that? If so, then I need to adjust my limits on my measurement to give me an alert when it crosses that. If you say, well, I really don't care about that, then SPC could be used for that. In this example here, you can see that, basically we had a huge problem that's hit, and so you got the alarm at about the same time. Okay, so these are just different examples on how SPC and SPC charts work. Now what I migrated towards was histograms. That's one of the ones I like to use, is to actually measure the distribution. And then I compare it to a normal curve, and then I can visually see the skewness and kurtosis. So a histogram, it really builds off of the knowledge that we've built up so far. And with a histogram, we are actually, well, this is what it says, is we can measure how normal it is, but a histogram is divided up into bins. Bins are, there's bins and bin width. I can remember when I was working with a mechanic, he had this whole big bench full of nuts and bolts and washers, and there's an intern, he goes, I want that sorted. So I built on a wall all these different buckets, and if this washer was this big, I flipped it in that bin if it was a bolt, and I actually built him a histogram of his workbench so he could go get, and so that sort of stuck with me. Every time I talk about histograms, we talk about bins, I have that vision of all those bins and we're flipping all those washers and bolts and nuts, and but it's not really that different. Is we have this data, and what we do is we take the range and say, okay, the data operates in this space, and then we break that into bins. And so what we do is every time the data goes into one of those bins, we count it. So the histogram is a count of how many pieces of data are in that bin. Now, the number of bins is a function of the number of samples in your data set. So you have to have an analysis window. And so it's the statistical relevant number of bins is equal to the square root of the number of points. So if you have 100 points, you have 10 bins. And then once you know the number of bins, you can calculate the width of each bin by the range divided by the number of bins. That's how histograms are set up in all of the stuff that we've made. So that's what I'm showing you here. I take this original data set and I take the min and the max, click, click, I take the number of points and I calculate how many bins, and then what we do is we say, well, how many points were in this bin? 2 points here, and so what you can see is the occurrence of points per bin looks a lot like our bell-shaped curve. But the bell-shaped curve is a statistical number based upon an ideal embodiment. This is a physical thing that's exactly what your data is. So what I like to do is, and this is where personal preference, some programs show it sideways like that, which there's value to that. Others like to flip it up and down. It's still a histogram. But what I like to do is align the histogram. So what I've done, a lot of times they're shown as a bar graph here. You can also connect the dots, and that's what this one is, the blue. And what we do is we show the blue with that pink picture there is what an ideal or a normally, for the statistics for that data. You know, again, when you're calculating sigma, skewness, kurtosis, average, mean, it doesn't know that the signal's not normal. It's just a math equation. So what we do is we take those numbers and then we back calculate what a normal signal would look like. That's what the pink is. So if this was ideal, it would be the pink. Blue is the histogram. The histogram is what it actually did. There's really no math in a histogram. It's just a sorting routine. So when you compare the statistics for a normally distributed data set and the actual histogram, visually you can see. So what's the which tail's got more data in it? The negative going tail, and it's got a skewness of very small, but you can see it's shifted just a little bit. And then you can see as the kurtosis is above 1 or above 0, it's positive. Okay, so it's a little skinnier. So it's a little skinnier, shifted, but it's not bad. And that's what you do is you put limits on how much you can have the skewness and kurtosis. And then when it moves outside that, you know your signal's broke. Something's wrong. That's all built in our loop analyzer, but this is how it works. Now that we have some basic understandings of average, max, min, range, sigma, skewness, kurtosis, those are great, and you can use those to identify the normalcy of your data, and if it's outside that, it's usually broken. There's a mechanical constraint, there's a signal that's broken, something's wrong with the data. You need to go investigate it. Now what's neat is we can start playing with this understanding of sigma and variance and use it to determine the likelihood that a signal is oscillating. We can calculate the signal to noise ratio. We can tell what ideal noise looks like. And that's what's called the correlation or the autocorrelation function. Mathematically, it's kind of scary, but let me try to hopefully illustrate how an autocorrelation works. Remember the variance calculation. The variance calculation is the sum of the error, which is the average minus each component squared divided by the number of samples. Okay, so now if we were to separate this top part into two, okay, do you see the squared term? All I've done is I've removed the squared term. Do you see how this equation and this equation are the same thing. Yep, they're the same thing. All right, that's step one. Step two is now let's add another parameter here, this L thing, this lag. I wanted lag. So here see the difference? I've taken this L. I don't like the term L, lag, but that's what it's called. L is the number of time shifts. So it's like, well, let me just finish this. So what we have here is we take a signal compared to itself at different time periods. And that's what we're going to try to answer. And then you normalize that by dividing. So if you go with lag 0, at lag 0, this top equation shrinks down to the variance. So what is lag 0 every time in an autocorrelation? 1. And so that's kind of something that we're going to be playing with, is it allows you to take any signal and reference it to 1, and then you can look at how it moves. And it gives you insight into the noise structure and the signal to noise. And it's very powerful, but you need to be aware of some of the limitations. So that's what we're going to talk about. I'll real quickly try to illustrate. If I take my hand, you know, I've got 5 points. And so I said, I want to compare my hand to itself. Now, well, it'd be like taking my hand to take a picture of it. Now I have a picture of my hand. Okay, now I'm saying, okay, now I want to compare my hand to itself. At lag 0 is I line up each digit. So what's the likelihood that this hand and this hand are the same? 100%. That's what an autocorrelation of 1 is. It's kind of like if you look in the mirror and you see yourself, that's a lag of 1. If you look in the mirror and see somebody else, that's a different problem. Now, what we have here is if we shift it 1 lag. Now you notice these two don't have anything to compare. So my data set shrinks by 1 or 2. So I'm now comparing, well, 4 points. So how well do those line up? So, well, it's kind of the same, but not really. But it's closer to 1 than, and then we say, okay, so it starts at 1, comes down. Now we shift it again and again and again. And so what happens is you are comparing the signal's tendency to repeat at different time shifts. That's very powerful when we get into how to analyze the signal to noise, and all that good stuff. And that's what I'm going to show here is our old friend, the sine wave. And this series of slides is kind of neat. So what you have here is a sine wave, and I'll just shift it 1 lag. I've got 2 signals right on top of each other, so you can kind of see now. The original signal is that black one, and then the whatever that other gray color is. When they're right on top of each other, you can almost, if you could plot them in a scatter plot, take the one signal is the x-axis, the other one's the y-axis, and then plot them, you would get a 45-degree angle. Slope 1. That's the other way I like to think about this. It's the rxx, is 1. That means they're the same signal, or the probability that one signal looks like itself is very, very high at lag 0. Okay, so we have a dot. Now let's shift it 1 time, or 1 sample, or 1 lag. So now when I compare those visually, they can look kind of the same. So if I were to plot this one versus this one, I'm still pretty close to a slope of 1, but it dropped just a scooch. Now it's 0.8. So it says, well, 80%. So I've got an RXX of 0.8. So it looks kind of like it did, but it's now shifted. And then we just start going across. Now you can look at the slope. It's dropping. Now when we get on a sine wave, we've shifted it to the point where I can't get any useful information. It doesn't look like itself. That's called a 0. 0 means the probability that that data set looks like itself has gone away. And so you can see I just like doing that. So you can see as we start with a 0, 1, 2, and then at the you can see at the dead time you're exactly out of phase. Or not out, well, you can see here when you shifted it to the dead time, now you have a mirror image. So you can see if you have a sine wave, what would you expect the autocorrelation to be? A sine wave. So what I'm getting at is once you characterize there's nothing you're going to see in an autocorrelation that is not in the original data set. It may sound silly, but you can't show something that's not there. It just allows you to tune your eye to see it more quickly. Maybe and this is an obvious one because it's a sine wave, but if you got a bunch of them going on, how do you tell what your signal is or what's your signal to noise? So that's what I like about the autocorrelation is I can look at a signal's tendency. Is it a fast moving signal? Is it a slow moving signal? Has it got a lot of noise? Is it cyclic? Is there multiple sine waves? And we can take a signal and compare it to itself at different shifts. That's called an autocorrelation. And there's really three. When I do autocorrelations, and this is how, when we're doing tuning and control validation, I'll look at the normal ebb and flow of a system on control. If a system's poorly tuned or sluggish, it'll look a lot like this top. It just takes forever for an error to be removed from the process. In this case, this is what's considered really good. It's when you drop to within what's called the confidence limits and you never come out of them. So the amount of time it takes to get in there is a function of the tuning. So if you've tuned it to be a nice first order, it'll just come down and stay. This bottom one is what's called an autoregressive noise structure, and it could be two things. The loop's unstable or overly tuned aggressively, or you've got a cyclic disturbance. Either one needs investigated. But when you have an autocorrelation that starts bouncing around, does this look a little bit like this? Yes. You have an oscillation. Something's going on that you need to investigate. This, I like to see this when I walk into a site that I haven't been for a while, and it's just, that's easy to fix. If I walk in and I see this, I really know I don't have a tuning problem. It's something else. If I see this, it could be a tuning problem or a process problem. The autocorrelation gives you hints as to what the next action should be. So we reference it as this. If the RXX is 1, that means it's the same, or it repeats at different time periods. The other way you can say is there's a 100% probability that that signal will look like itself at that many lags. If it's a 0, that means there is no information. Once you shift it once, and that's what ideal noise looks like. Noise is, I don't know if you can hear that hum, that white noise. If you could measure white noise, the first lag, all information's gone. And that's actually what you want in process control. When the signal is present, you have an autocorrelation that sort of ranges somewhere between 1 and -1. Now, the first lag of any autocorrelation is defined as the signal-to-noise ratio. So the rate at which it drops tells you how powerful your signal is. Now, in all of these autocorrelations, this is a statistical function. So we have confidence limits. And those confidence limits, because this is a statistical calculation, statistics is all about numbers and population size and all that stuff. So the more points you have, the more statistically relevant your autocorrelation is. Once you cross the confidence limits, you assume that the value is 0. I still like to look at the shape, even inside the confidence limits. Sometimes algorithms will show it. If they show a trend, sometimes they don't. But it's statistical in nature, and it's related to the number of points you have. So if you had infinite number of points, you'd have infinite confidence. That's what we're looking at here. So this one shows this shape, and roughly 3 to 4 shifts. It went into the confidence limits. And then from there on, it's considered noise. So there's no useful information once it gets into the noise band. The trick with process control is to get it from a 1 to the noise as fast as you can without going unstable. And so if you can imagine a loop that's tuned very, very slow, it'll take a long time to get there. If it's tuned perfect, it'll shoot in very fast. And if it's tuned oscillatory, it'll oscillate. So by looking at the autocorrelation with a process control perspective, you can sort of see how aggressive the control loop is tuned. Now we get into autocovariance. Covariance and correlation are virtually the same thing. If you go back and look at the equation, they're almost the same, but we don't divide by the variance. So in covariance, it's actually the variance of the data set. That's where it starts. So if you look at this, at lag 0, you have the variance. On correlation, at lag 0, you have a 1 because you normalize it by the variance. So if you autoscale them, they look exactly the same. Sometimes if I'm doing a before and after control evaluation, I'll use covariance because you can see the energy in the signal stops, and it's a real neat comparison. That's where if you use autocorrelation before and after, it can amplify the very thing that it makes what you did look different. So I like to sometimes use covariance when I'm doing comparisons before and after. I like correlation when I'm trying to normalize and look at a bunch of things at once. Now this is showing in variance terms. You can see it starts. So they look exactly the same. Now here's showing an example, a real life example where we would take our raw data and run it through our autocorrelation. So you can see at lag 1, it's the same signal. This thing would have a signal-to-noise ratio of about a 0.75, and then it drops down to the confidence limits, but then it comes back up. Then it goes down and it shoots past. This is what it's not normal, and it's got an energy signal that could either be tuning or it could be a process disturbance, either one. But normally when you see an autocorrelation, it should start at 1, shoot down to the complement and stay there. It should look like this middle part for the whole time. So when you see that it kind of floating around, I like to think of that as just the process is allowed to float around. You know, remember process control, if you can imagine like that piano string, if you pull on it, it pops it right down in. And if it's allowed to flop around, that's what this looks like. Now, when we're comparing two signals, so for example, if I were to compare my hand to my foot, that's a cross correlation. They kind of look the same, but they're not. Why would we do a cross correlation? Why would you compare two signals that have nothing to do with each other? Well, the cross correlation would tell you exactly how much they have to do with each other. And that's neat when you're trying to find dependence or causality. What happened first, second, interactions, dependencies. There's cross correlation is really neat for that. Now, it's very much like the correlation equation, but here we are using X to represent like my hand and Y to represent my foot. They're two different signals. And then we shift them. Mathematically, it actually looks like this. If you were to look at the how the algorithm works, you start off with the original two signals, and you plot them against each other, and you come up with the slope of that, and then you start shifting one of them. So eventually you get to where you're shifting two different signals. And that's why with a cross correlation, your statistical relevance is actually pretty short. Once you shift much past, well, you can see, I'll show you a picture. Now this shows two signals that are dependent. So when you're doing cross correlation, and I'm going to talk about a one-sided cross correlation here. Two-sided cross correlation, you literally would take your original signal, and one-sided, you just shift one signal out. Two-sided, you shift this one out, then you shift this one out. Okay, so you get two sides. It's when you don't know which is the dependent and independent signal. The independent signal is sort of like the starting point, and the dependent signal reacts to it. So if you shift the dependent signal in the direction of the independent signal, you'll get a hump where they correlate really well. If you're backwards, you get no dependence. So if you don't know independent or dependent, you need to do a two-sided cross correlation. If you have some knowledge about which one came first and second, then you can reduce the mathematical rigor and only do half of the shifts. So what we're seeing here is a one-sided cross correlation where we have two signals. So if you look at these, you can see the green is the dependent signal and the blue is the independent signal. And so if you slide the independent signal over, that's what we're showing here, as this moves over, we get you can see the correlation shoots up. And so, I sometimes, you can't just look at one point because the math is applying all the points. But sometimes I'll pick a section and see if I shift it and see them line up. And that's what we're seeing here. This sort of lines up here at some time frame different. And you can see it. And so here this is showing that we have a positive correlation between, that means there's a dependence. And then I can look at the ratio there's what, a 0.3. That's roughly 30% of the dependent signal is a function of the independent. So if your quality measure is the dependent signal, you should fix the independent signal. Fix it and your problem will be reduced by 30%. That's what I like about the cross correlation. It gives me some indication of what to do. I can't fix everything with control. Sometimes I have to find the source and take that out. That's what I like about the cross correlation. So if I zoom in on that cross correlation, it shows me that roughly 8 lags or 8 samples, those signals look a lot alike. Not just one point, the whole shift looks a lot alike. And this is what I've done is I've actually taken, this is kind of hard to see, but if I take these two signals and then shift this one over 8, that's what this shows. You can see the blue has been shifted. Now do you see how they kind of look the same? That's the trick. Is cross correlation allows you to see where both signals kind of look the same, and that's the dependence. So you can either fix it with control or remove the source, fix the source, and that's what I like about cross correlation. With cross correlation, the confidence limits they're not totally a function of the number of points. It's this inverted U that you can see right here, which means is your confidence goes way down as you shift the data set. So once you get past a few shifts, that's all you really care about with a cross correlation. Is like you can't, if you have two signals and they're dependent 2 hours apart, well, that might make sense, but you have a different sample period, so that would change your whole picture. So what we're trying to say is once you shifted a few, outside the normal delay times of your process, you don't need to keep shifting it. Now the math, when I compare the equations, just for you guys that like the math, the autocorrelation, you can see this was your variance, and I split that apart and you divide by the variance. So you start with a 1 on autocorrelation. You can see the covariance, or the autocovariance, we don't normalize it. So this one starts at the variance. Cross correlation, it starts, you divide it by the sigma of each value. So I'm really looking at a shape, and the percent, it's almost like how much of that signal is influenced on the other. And then cross covariance is we don't normalize it. So again, this one I pretty much use cross correlation because I'm just looking for a shape and what fraction of that signal is in the other one. And then for covariance, I like to use it if I'm comparing before and after a correction, because what you want to do with control is remove the energy. So you don't want to amplify the noise by doing off and on comparisons with an autocorrelation. But I like to use autocorrelation when I'm first starting off to kind of see what the ebb and flow of the process is. So that kind of gives you a picture of when you take two signals and compare them, even if it's itself or two different ones. Now here's some examples of a cross covariance. Again, here's we've got two signals here, and you can see that there is some dependence. They're out of phase. This is actually a temperature control where we have our steam pressure going up and down, and as our heat goes up in the drying section, our moisture drops. So you can kind of see there's a dependence. So when I do a cross correlation and slide this over, you can see that I have a high negative correlation because we have a negative process gain. And then if I shift this a little bit further, they'll be back in phase. So here you can see that our cross correlation has an oscillatory effect on the process. That's a big deal. So we can say, well, how am I going to fix this problem? That's my that's my dependent variable. So I could spend all day trying to fix this when really the independent variable has a high degree of correlation. And so it's like, don't troubleshoot at this, fix that problem, and that'll go away. That's how fast you can get to an answer. This is showing it actually shifted. So I've actually shown here is at the most negative point, it's 18 shifts. So now if you look at them, see how the humps and valleys all line up? Remember, it's not just one point, it's the entire signal. Now on the bottom, I went over until it was the highest positive correlation, which 55 shifts. So you can see I've shifted over 55 samples. Now notice that the positive humps, that's what we're looking at. The positive humps compare or the negative compare. So when you're looking at a cross correlation, you really need to actually see the signal shifted, and that's what we can do with this software. Is it allows you to see, is that really there? And then you're like, oh, well, if I go fix this parameter, then the other one will just get better. It's not a tuning issue. It could be at this loop, or it could be some disturbance, or in this particular one, they had changed the main valve, thrown in some default tuning, and it just was banging all over the place. So we fixed that, and the whole machine calmed down. Now, I just want to illustrate, a lot of people say, well, the max correlation is the same as the dead time. That's wrong. So what I want to look at here is a bump test. So here I've done a bump test. Here's my up, down, back up, and you can see I've made a perfect first order response. Now, what you have to look at when we do a cross correlation, we're correlating two signals, is how far do I have to shift the actuator over to the process before they look the same? And in this case, I shifted it to that point, which was 20 lags, okay? Now, if I look at my model, I use a 15-second delay, a 5-second time constant, and a 1.5 process gain. Have you figured out what the max correlation is? It's not the dead time, but it's the dead time plus the time constant. So if you shift them, look, this is the point where, do you see how they kind of look the same? I've modeled the red line showing the shift. So when I shifted at 20 lags, that was the point that I had the minimum difference between the two data sets. That's the max lag. And some auto-tuning algorithms that try to identify it, they will look at the cross correlation, find that peak, and say that's equal to the sum of the dead time and time constant. And that provides them with a constraint when they try to figure out the other parameters. So it reduces the problem state. I just wanted to show an example of how that works. Our last thing, and we'll spend a short time on this, is performance measures or performance indices. There's integrating absolute error, there's integrating square of the error, there's integrating time absolute error, and integrating time square of the error. These are simply measures to show how long a measurement is above or below a particular reference signal. They're just different performance measures. I've used these to measure, like if I'm changing the set point, it takes a long time. It's the area between the set point and measured value. So I'll have a big number, and when I improve it, that area drops. So the amount of time that drops, or the ratio, is a measure of how well your performance did. These are just sort of classic performance measures that you'll see in a lot of different statistic evaluations. Is they'll take two signals or a signal compared to its average, and they're integrating the square of the error or the absolute value of the error. It's just a measure. And with t, it has to do with the sample time, and it pulls that into place. So all these are just different ways of measuring a performance measure for a particular data set. The thing to remember with these is you have to reset them because they average forever. So that's one of the issues, is I usually do it on a data set, and then if I do another one, I have to reset it, and then I compare the differences. We've covered a lot of ground in this particular session, and it's all related to statistical analysis of a data set or two data sets. We covered a sine wave and how to calculate a sine wave, what the amplitude and the period. Peak to peak is the range, the average, the DC component, the median. We talked about the mode, the most frequently occurring data point. We talked about variance and how to calculate variance, and that variance is related to the amplitude of the data set if it's a sine wave. We talked about sigma, or standard deviation, but that's a measure of how normal a data set is. Remember the 1, 2, and 3 sigma, and what those values are. 1 sigma is 68%, 2 sigma is 95, and 3 sigma is 99.7. So those are just telling you statistically where your data will be. We talked about control charts and how you can use those to help you better define what an alarm is. Then we went into kurtosis and skewness. It's the way to measure how normal your data set is, and we talked about how you could relate those to physical problems in your process if it's not normal. Then we looked at a histogram and said, well, I can actually measure my distribution and then compare it. So now we can start using histograms to kind of measure the bins and the bin width. Then we realized we could look at autocorrelation, see how a signal changes over time and give us indications of signal to noise, energy. We could tell if it had a value of 1, that the signal had a high probability of looking like itself after those time shifts. 0 means there's no useful information. A -1 is it's inverted. We want our goal in automation to get within the confidence limits as fast as we can, because that's where noise is. That's white noise. We realized that a sine wave is also a sine wave in the autocorrelation. That's one thing that we were seeing, and then we went into variance and cross correlation, and then we ended up with performance measures. You're not going to see information that's not in the raw data. But if you're new to this, you look at raw data, it's hard to decipher what it is. But by applying these statistics, it can tune your eye to what a normal system looks like. It can show you what kind of problems you're having. You can link them to physical problems in your process, and you can look at the ebb and flow to determine and use these for troubleshooting. This is the statistical tools in my toolbox that we use. And there's not one that's my favorite. I'll use them depending on the problem I'm trying to solve. These are the kernel knowledge that apply to higher level KPIs, trending, and looking at large amounts of data very, very quickly. That's statistical analysis.